This is CPE 233, Lecture 19. We're going to talk about interrupts, which is going to be primarily a review, but then we're going to get into practical applications somewhat in Experiment 7. So this is the RISC-V microcontroller, as we talked about it before. Most every signal on here has to do with I/O, except essentially the reset and the clock signal. All the other signals have to do with I/O, including this interrupt signal. This interrupt signal connects to it's a pin on the microcontroller. It is intended to connect to some external device. So two types of I/O that we've been working with, or that we will work with. We've been working with memory map, but now we're going to be getting into interrupt-driven I/O. And so once again, these allow computers to interact with the outside world in an efficient way. So memory map is fine, but interrupt-driven programs give us kind of a new and potentially better way to do I/O. So computers, generally what they do is they wait for you to do something, and which is the kind of the theme for embedded systems, where it's waiting for you to do something. When you do something, you want it to act immediately. So you want it to be really responsive. You want an appropriately designed system. You don't want to over design it or under design it. Either way, it's going to have issues. And most interesting here, we want to keep the throughput high in any system we have. So keeping the throughput high is kind of a generic term. Generally speaking, in embedded systems, what we want to do is make sure it's okay to do something stupid, but don't do something stupid. Don't execute stupid code if you've got something really important to do. There are going to be times in embedded systems where you don't have anything important to do, so it's okay to do nothing. Two approaches to designing digital systems you can have, with microcontrollers in it. You can have the microcontroller do the work, or you can offload some of those tasks to external hardware. And so the interrupts support the offloading of tasks to external hardware. Essentially, it gives that external hardware the ability to tell the microcontroller that, hey, I'm done with this task. And that's opposed to the microcontroller continually asking the external hardware whether it's done or not. If you had to do it that way, it would be wasting clock cycles and lower the throughput. Typical ways to do something here, or react or have the computer respond to something, is polling, essentially asking, like for example, asking a button whether it's been pushed, or we could connect that button to the interrupt and just have that button essentially tell the microcontroller it's been pushed, and that's going to be our interrupt-driven approach. This is our typical polling code, which means this is the polling loop. It's going to be stuck in that loop forever. It can't do anything else until it gets until someone presses a button. So not necessarily bad, but this approach does have issues. Once again, we're going to work with interrupts, and the idea here, the highlights of this, it helps you avoid polling if that's important, if you do have something better to do, and potentially it increases the response time to reacting to external input. Interrupts, not a big deal. It's very similar to subroutines. It's just a little slightly different mechanism, but the theory is the same. So we are in the support of interrupts here. We have these three registers, and we're going to also add this other module here. This other module, you don't need to know a ton about this, but you should know that inside this module there are three registers. Two of these register values are output, and then one these registers only has 1 bit output, and we'll get into what those reasons are later. But you've seen the programmer's model. Now we've got 3 other registers in there that are important to know. Interrupts are very similar to subroutines. Idea of a subroutine is, I call a subroutine under firmware control. And what happens is I store the place to come back to after I execute that subroutine. I store that in the return address. So interrupts are the same thing. I have to store the place I need to come back to. I store it somewhere, but I'm going to store it in one of the CSR registers, which is the CSR MEPC register. Okay, so the next thing I do in a subroutine is I tell it where to go, which means I load the address of the first instruction in the subroutine into the program counter. Very similar to interrupts. I need to go to the interrupt service routine, so I'm going to load the address of the interrupt service routine into the program counter. So you process what you need to, and with a subroutine, I exit it with a return instruction. With a interrupt, I return essentially with an MRET, which is a machine return. And what happens when I execute a return instruction, it takes that return address that I saved, puts it in the PC. When I execute an MRET, it takes the return address that I saved in the CSR register and also puts that in the PC. It's very similar. So we're going to crank through this program, I think, very quickly. We've done it before, and it's not a big deal. I don't want to waste time on it. We'll do an example later on this. And so this is the idea on this program is it's interrupt driven, and anytime it receives an interrupt, it toggles an LED, and it calls out the rightmost LED. So the structure of this program is essentially, I've got to first put the address of the interrupt or service routine into an MTVEC. I do so using this new instruction here, which is CSR read-write instruction. I need to do some other stuff here also, but I need to enable the interrupts, which is setting a particular bit in the M status register, and then I'm stuck in this polling loop. So this is a polling loop, no big deal. This is an example program, but what happens is the only way I can get out of this loop is essentially to get an interrupt. Inside this interrupt, that this bit here is going to be set, and that's going to break me out of this loop, and I can go down and do other stuff. But the other thing I do inside this interrupt service routine is I turn the interrupts off. I mask them, I disable them. So the interrupts return from this disabled when I hit the MRET instruction. So when I return, I'm going to break out of this loop, go down here and do something, and then what I'm going to do here is two things. I'm working with a flag. I'm going to clear that flag, and then more importantly, I'm going to execute the CSSR read set instruction, and it's going to re-enable the interrupts just like it did up here. This is the new state diagram associated with the control unit state machine. What's interesting about this, you should study this in depth, but what's interesting to us is interrupts can come in any time, but they're only processed when the microcontroller completes execution of the current instruction, and you can see that in here. So the only time you're going to go to the interrupt is in one of these cases, and this is for the non-load instruction, and this is for the load instruction. More importantly, the microcontroller completes execution of the instruction that it's executing when it gets the interrupt before it processes the interrupt. There is an interrupt state here. There's like 4 things that happen in that state, and we can do them simultaneously. We only need one state for the interrupt, and this is interrupt state, interrupt cycle. It goes by a couple different names. So when you get an interrupt, 4 things happen. First thing I do is I mask the interrupts by clearing the MIE bit in the M status register. Before I do that, I'm going to copy that bit to another bit in the M status register. I'm going to load the address of the next instruction into the MEPC register, and then I'm going to load the PC with the address of the interrupt service routine. So MTVEC has the address of the interrupt service routine. It's usually the first thing I do is part of initializing the interrupts in a program. When I'm done with the interrupt here, what I'm going to do is issue the MRET instruction, and 2 things are going to happen. It's going to take that stored return address, put it in the PC, and it's going to copy this MPIE bit back to MIE. So if I do have a chance in the interrupt service routine, as you've seen before, um, to modify this bit, and we'll be doing that quite a bit. And this is the complete diagram. And moving on here, like I said, we do have the ability to turn the interrupts on and off, which essentially means allows the microcontroller to act on the interrupts or not act on the interrupts. And we do this via one bit in the M status register, and we call it the MIE bit. It's bit 3. Essentially, when that bit's a 1, it allows for this. This is the bit right here. If this bit's a 1, it allows for data to pass through that AND gate. If this bit is a 0, no data passes through that AND gate. So interrupt-driven program structure, we need to initialize stuff as in a normal program, but now we need to initialize interrupts as well. Generally speaking, we have the main code, which we call the background task, and then the interrupt service routine code, which we call the ISR code, or the foreground task. So generally what's going to happen is I'm going to be cranking out, it's going to be executing instructions in the main task or in the background task, and it's going to get an interrupt, and it's going to switch over to the foreground task. Okay, so that's going to be interrupted. It's going to switch to this new code, execute this new code, and then go back to wherever it was when it got the interrupt in the main code. Yes, so the control registers, control and status registers for supporting interrupts, there's 3 registers there. This holds the interrupt enable bits. This holds the address of the interrupt service routine. This holds the return address. So when you act on an interrupt, it knows where to go back to in the background task. So there's 4 new instructions we need to implement here. One of them is this instruction, which is control status register read write. It allows me to write this register to a register that I call out in the CSR. And typically we use this to write the MTVEC. Also, it simultaneously reads that value, but typically we will just stick a 0 in there because we're really not interested in that value. The other instruction you need to implement is this MRET instruction, and what it's going to do is take the return address and stick it into the program counter. It's also it's also going to do something else. It's also going to take CSR M status and I'm just going to put it's the MIE bit. It's going to take the MPIE bit, which is a bit in the M status register, and it's going to copy it to MIE. 2 other instructions here is we want the ability to set and clear bits in a register, and these are our instructions that do that. So what happens is we are going to, this is the control status register read and set, and this is the read and clear. And you can see that the setting of a bit always has to do with an OR operation. You can see that OR operation right there. A clearing of a bit has to do with ANDing it with 0. You can see that AND operation right there. So this gives us the ability to set and clear bits within individual registers within the control and status register. So experiment 7 is essentially to add interrupts to experiment 6, and this is the last thing we need to do to the adder. Now we're done after this. So the approach you got to do here is got to understand what's happening in the interrupt architecture so you can actually implement it. You got to make the changes in hardware, and then you're going to test it. Simulation only, you're going to test it, test your hardware. Okay, once again, it's simulation only. I provide the program. Here's your test program. Essentially what this program does is kind of what you'd expect, and you want to see everything happen here. Here are the register. Here's the MTVEC being written with the address of the interrupt service routine. Here are the interrupts being enabled. Here is a polling loop. Here is the interrupt service routine that set the flag. Also in the interrupt service chain, I'm clearing the MPIE bit, which is going to ensure that this, when the ISR returns, it's going to return with the interrupts disabled. That's all good because I can re-enable the interrupts, which I do right here. Okay, so you want to show that in your simulation output. You're required to give a simulation timing diagram, which I want very nicely annotated to show that this stuff actually works. You need to see all these circled stuff happen inside the simulation. Now the key to making this work is when you simulate it, don't give yourself an interrupt until the interrupts are enabled. So you got to wait a while before you give it an interrupt. And you got to make sure everything's all initialized and the interrupts are enabled before you give it an interrupt. So you're in charge of, giving it an interrupt sometime via the test bench. So this is a file that that you can essentially I call a listing file, and it's quite useful because it has both the addresses and the instructions here. It's a little bit tough to see because it's switched over to the aliases for the registers, but not a big deal. You can see that here's a CSRRW instruction, here's another instruction, another one, and another one. These are very important. This is enabling the interrupts. This is your polling loop, and you want to be able to show that this stuff is actually working in your simulation via your test bench. So once again, it's the whole idea of Experiment 7 is just to prove that your interrupts work or that your modifications to the hardware work. You're going to write the test bench. First thing you do is reset it, and then you wait a while. You wait for the interrupts and everything else to be enabled, and then you generate an interrupt. And at that point, you got to show that all the right things happen with when you get an interrupt. And you're actually going to return to the background task, and you're going to make sure the interrupts get re-enabled as well. And you can see that right here. You're going to definitely want to show that to see that interrupts are re-enabled before it goes back to the polling loop. So this is an example. The example we were going to do on a separate video. And that is all.